In this video, we're going to show you how to perform two sample tests for population means under a couple of different scenarios. We're going to also show you, through example, how to compare means of 3 or more population. So let's get started. The first example is about testing the population means when we have two independent samples. Here's an example. Responses from a customer satisfaction survey for 2 stores are being recorded here. So we have a sample from store 1 and we have a sample from store 2, and we want to see whether the means are either the same or they are different, or one is smaller or bigger than the other. So we have the raw data. So the first thing we need to do, of course, is to summarize it into a number of statistics that we would use to perform the test. The 3 statistics for each of the sample that we need to do, of course, is the sample size, the sample mean, and the sample standard deviation. Now, in order for us to do that, the best way, of course, is to define the data, the area for the data, so that we can actually just use it as the reference. So we would define the first sample as sample 1, and then we would define the data for the second sample as sample 2. And once that is done, then we can use Excel to calculate the sample size, the sample mean, and the sample standard deviation. A lot of times, these 3 statistics for each of the sample is already given to us. So we don't have to do that. Now, before we actually go into the calculation of statistics, if you think about it, how do we know that the 2 samples are independent samples? Well, the criteria for in the sample is the fact that there's actually no overlap between the population that we are taking the sample from. So if you think about the 2 stores, the customer base from each of the stores theoretically has no overlap. So if we take a sample, the sample should not have any overlap as well. On the other hand, if you look at the sample size, we can see that the sample size could be different for the 2 samples, and that's also a hint that the 2 samples are indeed independent. So now let's summarize the samples into the 3 statistics. So the first one is the sample size, and the way to do it is to do count sample 1, and that's 34. And then the sample 2, of course, is count sample 2. So if you define the area with a name, you make the typing so much easier. So now we calculate sample mean. The sample mean, of course, is the average, sample 1. And then the mean for the second sample is average of sample 2. And finally is this sample standard deviation. And in Excel, as we talked about a long time ago, this is STDEV sample 1, and then STDEV sample 2. As I mentioned before, a lot of times, we make a mistake in terms of the typing, sample 2. As we mentioned before, a lot of times when we do a problem, these 6 statistics is already given to us, and then we can actually do not have to go through this step. Now, in order for us to test the hypothesis that the mean satisfaction score for the 2 branches is not the same, what we need to do is, of course, is to go through the 5-step hypothesis process. So the first step, of course, is to set the hypothesis. So how do we set the hypothesis? Well, we define the parameter first, right? So the parameter was be mu1, which is the mean satisfaction score for the branch number 1 or store 1, it doesn't matter. And then we can just copy the same here. And this mu2, of course, is the mean satisfaction score for branch number 2 or store number 2. And therefore, let's write down the research hypothesis or the alternate hypothesis. The alternate hypothesis mu1 is not equal to mu2, right? So because we want to test the hypothesis that the mean scores is not the same means it's not equal to, right? So now that this is the alternate hypothesis, the null hypothesis, of course, is they are equal to. Okay, so that's very straightforward. And because of the fact that this is not equal to, so this is a two-tailed test as before. Right, now, the second step, of course, is to set the level significant. And usually, if you don't have any particular feeling about how serious the problem is, we will set alpha equal to 0.05. And it actually, in reality, it doesn't really matter. We can actually look at the p-value since we are using the p-value approach and see how small the p-value is. The third step, of course, is to set the rejection rule. Since we are using the p-value approach, the rejection rule is always the same. So we say reject x0 if the p-value is less than alpha, which is equal to 0.05. Now, most of the work, of course, is done in the fourth step, which is to calculate the test statistic and then the p-value. The formula for calculating the test statistic is x1 bar minus x2 bar minus d0 over the estimate of the standard deviation, which is S1 squared over N1 plus S2 squared over N2. Now, this is in statistics from a theoretical perspective, this is actually an approximation. The exact solution of this problem is still not totally known to us. So D0 is just in case that we want to test where the difference of the two means is equal to a particular number, then D0 will be non-zero. In most cases, D0 is 0. So if you look at the test statistic, it's just like what we have before, right? You compare what you see from sample 1 and what you see from sample 2, and then you take into account the availability, which is an estimate of the standard deviation in this case. The calculation of the test statistics, of course, is actually not a really difficult problem. We can actually do it by hand. However, because of the fact that this is a t-test, we need to calculate the degree of freedom. The calculation of the degree of freedom is actually much more involved, right? So you can see that this is the approximated degree of freedom. It involves S1 squared, which is the sample variance, N1, which is a sample size from sample 1, S2 squared, N2, and then you square it, and then you have all these things. So that probably is best to use an Excel formula to help you in doing the calculation. The thing that does not show here is that after we calculate this, this is likely to be a number that is not an integer. If it's not an integer, the proper calculation is that we would actually round it down, right? So if you have 60.5, then the degree of freedom that you should use is actually 60, right? So we should always round this down. Now I'm going to show you how that is done. So you can see here that I already have the formula set up. So by the time we input the 6 numbers, the variance, which is S1 squared and S2 squared, are already calculated for us. The degree of freedom is calculated for us. So if you look at the formula, I have input this formula in Excel, and I use a function int to actually round the number down. Int means that you take the integer part of the final number, which is basically rounding the number down. And I also, in this part of the worksheet, I also calculated the test statistic. The test statistics is actually not too bad, right? You compare the means and you divide it, you compare the means and you divide by the estimated standard deviation in the format of s square root of s1 squared over n1 plus s2 squared over n2. So if you can use Excel and Excel formula, these things can be done quite quickly. Okay, so now, so how do you calculate test statistics? Well, the test statistics, as we show you over there, is already calculated for us. Is equal to negative 1.389. So what is the p-value? Well, what we have to think about is whether this is a one-tail test, two-tail test, or two-tail test. It's an upper tail test or lower tail test, or two-tail test. So in this case, because of the fact that this is two-tail test, we would take the small tail area and multiply by 2. Again, we're going to look at negative 1.389. Negative 1.389 is here. Right, so 1.389 is here. So this is negative 1.389. We will calculate the area and we multiply by 2. So how do we do that? Well, in Excel, we can actually do just this, right? So the p-value, let me just write it down for you, is equal to, right? So t dot dist, right, negative 1.389. And then the degree of freedom, of course, is 69. That is calculated using the formula. And this is 2, which is the calculated number, right? And because of the fact that this is a two-tail test, we multiply that by 2. So the p-value is equal to 0.1693. And so therefore, because of the fact that the p-value is not less than 0.05, so we would not reject, right? So we say since the p-value is not less than 0.05, we do not reject x0. And as we always do, we say we have insufficient evidence. If you reject, we say sufficient evidence. If we do not reject, we say insufficient evidence to conclude. And the conclusion is always about HA. So HA is that the two mean satisfaction scores are the same. They're not the same. Not the same, right? So this is always about HA when we draw the conclusion. So this is how we do the 5-step process. The complication, of course, is in the calculation of the degree of freedom, as well as to a lesser extent, the test statistics. So if you want to do the same problem using the critical value approach, of course, the hypothesis would be exactly the same. You would define the hypothesis the same way. You define the parameter, and then you define your HA, and sorry, this is X0. We kept ourselves, so this is X0, and the same thing here. So X0 is they're equal, XA is that they are not equal, and this is again a two-tail test. Alpha is the same, so we're going to just copy alpha equal to 0.05. As you can see that in this particular example, we just forgot to talk about, right? So it doesn't matter what alpha is. Alpha is equal to 0.05, you do not reject. Alpha is equal to 0.1, of course, you do not reject. So in this problem, the usual p-value that we would use in hypothesis testing would lead to the same conclusion in that we would not reject the null hypothesis. Now, the rejection rule, if you use the critical value approach, is slightly different. First, we have to calculate the degree of freedom. The degree of freedom is calculated here, equals 0.69. And because of the fact that we actually have a, let me just make it smaller. We actually have a two-tail test, so we're going to have to worry about the critical value on the lower tail as well as the critical value on the upper tail. So let's just write this down first. The degree of freedom is equal to 69, and the critical value, of course, is is equal to, you can actually use the Excel, this is INV, TINV. If alpha is equal to 0.05, so this area is together is 0.05, so one side is 0.025. So for a two-tail test, then you need to spread the alpha in two parts. So the lower tail is 0.025. So we need to find this point for the t distribution where the lower area, area of the lower tail is 0.025. So we'll say 0.025 because alpha is equal to 0.05, and it's a two-tail test, and the degree of freedom is equal to 69. Okay, so the critical value, of course, is negative 1.995. Now, you can also use the t-table. We actually have the t-table in also created, right? So if you want to use the t-table, you go down, you find the degree of freedom equal to 69, and then you go across, and you find a number that is equal to 0.025. So the number that we will end up picking up from the table is also 1.995. 1.995, of course, is the upper tail. And but because of the fact that t distribution is symmetric, so this is 1.995, this is negative 1.995, and so the rejection region would be reject x0 if t is less than negative 1.995, or t is bigger than 1.995. Okay, so that's how you put together the rejection rule if you are using the critical value approach. And the test of T6, of course, is calculated as we have done. The test of T6 is negative 1.389, right? So negative 1.389. And now we are in a position to make decisions. And if you compare this number, this is the rejection area, and negative 1.389 is here, and negative 1.389 is not in the rejection area, so we do not reject. So we say, since t is equal to negative 1.389 is not less than negative 1.995 or greater than 1.995, so we do not reject x0. And then we can actually write the conclusion as we have done before. So this is how you do a hypothesis test when you are trying to compare two independent samples. As we said, I just want to make sure that we understand when is it that we have two independent samples, when the population from which we sample has no overlap. So for example, if you take a sample of houses in Toronto and a sample of houses in Vancouver, you want to compare the prices, well, that you have two independent samples because you won't have any houses that is both in Toronto and in Vancouver. So you need to think about whether we have two independent samples from a conceptual standpoint. The other way of looking at it also is that when you have two samples and the sample size are not the same, and therefore they probably would be a two independent sample. The last thing we want to show you is to also how to use the data to construct a confidence interval. The formula for constructing a confidence interval is very much like the test statistics. You compare the sample means, and then you have the margin of error. The margin of error involves the t critical values as well as the estimate of the standard deviation. So in our problem, if you do a 95% confidence interval, would be really easy. Would be first of all, you take the difference of the mean. The mean is 6.882 minus 7.342, right? So 6.882 minus 7.342, right? Plus or minus. And then if it's a 95% confidence interval, again, you should always draw a picture. That means if the middle is 95%, so the middle is 95%, the outside is 5%. And so therefore one side is 2.5%. 2.5% again is actually the same value that we got, right? So this is actually correspond to the tail area equal to 2.5%. So the t value that we're using here is 1.995, right? So 1.995 times the square root of, right? So don't forget this is sample variance divided by N1, sample variance divided by N2, right? So you should take 1.683 divided by the sample size, which is 34, plus 2.285 divided by 38, right? So notice that I'm using the variance 1.683 and then 2.285, right? So if you're not using the variance, you have to use 1.297 square and then 1.512 square, which would equal to these two numbers in the formula. Okay, so this is how you construct a 95% confidence interval using, again, these 6 statistics that we can summarize from the data. So this is a typical problem that you would face when you have 2 samples from 2 independent population and you want to compare the population mean, either through hypothesis testing or through confidence intervals. Now, there is actually another way of doing this problem if you're using Excel's data analysis add-in. So this is what we're going to do next. We have the same problem. We have, again, the data from store number 1, from store number 2, except that we don't want to do all the calculation because of the fact that we already have the raw data. We can actually use Excel's data analysis add-in. And if you have the data analysis add-in installed, you click on data and you can click on data ribbon, you can see that the data analysis program is already installed for you. If you don't, then you can go to file, you can go to option, you can go to add-in, and then you can just do Excel add-in, click go, and then you just click on the analysis 2-pack, the first one, and you would install that particular add-in. Okay, so if you have it, so all you have to do is click on it, and then there's a lot of program that you can see. We have already in some other video demonstrate how to use the descriptive statistics add-in and so on. And so you go down, you can actually see there's a number of t-tests, and what you need to do is to be careful in terms of which one that we're using. The one that we should be using is t-test 2 sample assuming unequal variance, because in practice we shouldn't really assume that the variances are equal. So there's no basis for us to make the decision most of the time. So we should actually use the t-test 2 sample assume unequal variance. That's the program, and that program corresponds to what we just did. So we click OK. All you have to do is to specify the data. So you say, okay, the first set of data, of course, is from A1 to A35. And the second set of data, of course, is from B1 to B39, right? And then just like any other data analysis add-in program, you need to just fill up what you need to do in terms of the input. Now, there's something called the hypothesized mean difference. That's the D0 in the formula. If you are testing whether the difference of the mean equal to a certain number, that would be the number that you put in. As I said, in almost all cases in practice, this number is 0. If it's 0, we don't have to specify that. Also, you should tell the system that your first row is the name of the variable, or in this case, the name of the sample. So labels in the first row. So these things should be checked. Otherwise, you would be missing one sample point, and that's the common mistake that people make. So if you have names in the first row, make sure that you check that. And then you can also specify alpha is equal to 0.05. The default is 0.05. And later on, you can actually see that there's some significance in terms of why we actually do that. Now, you can put your output in many different places. I choose to just put it here. so that I can actually take a look at it. You can actually put it in a new worksheet if you want to, and then you say okay, and here we go. So this is the output, and you can see that the output actually calculate everything for you. So if you generate the output, you practically do not have to do anything. What you have to do is to go through the process of either the hypothesis testing, as we demonstrated, or the confidence interval process, as we demonstrated. So let me just walk you through. Let me just walk you through the output. Right, the output give you the mean, right, 6.882. Let me just maybe format this to where's the format, to 3 decimal places. You can actually see, and then also this is 3 decimal places, so we can actually see much easier. Right, so the mean, the variance, right? Remember we have 1.683 to 2.285. That corresponds to what we have here, 1.683 to 2.285. So it's already calculated for you. The observation, that's the sample size. Now, notice that the degree of freedom is different. This is actually a bug in Excel that has been around for a long time. Excel just round the degree of freedom instead of round down the degree of freedom. So a lot of times there is a difference between what you would get if you do it manually and what you calculate in Excel. I would not make any adjustment. If you're using Excel, just use 70 instead of, take the number and multiply by minus by 1, because you don't know whether Excel actually round it down sometimes. And if you do that, then you would make a mistake. So most of the time, almost in all cases, it actually does not really matter whether you use 69 or 70. So if using Excel to generate this output, you just use 70. The test statistics, of course, is the same. What the good thing about Excel is that based on the degree of freedom of 70, it actually gives you the p-value as well. Now, which one is the p-value? Is the probability, right? The two probability, one tail, probability two tail. So Excel does not know whether you're doing a one tail test or a two tail test, so it gives you both, right? So this is the p-value for the one tail test. This is the p-value for the two tail test, right? So according to Excel, if you're doing a two tail test, the p-value is 0.169. Now our p-value is 0.169 as well. So you can actually see that even though the degree of freedom is 70 instead of 69, the result is very, very close. So it does not really matter. In addition, Excel also gives you the critical value as well, right? So because if you want to use the critical value approach, you can actually use the output of Excel. Again, Excel does not know whether you're doing a one tail test or a two tail test. So you give you both, right? So if you're doing a one tail test, this is the critical value that you can use. If you're doing a two tail test, this is the critical value that you would use. Again, our value is 1.995, right? Based on a degree of freedom of 69, based on a degree of freedom of 70, the critical value is 1.994. So it actually does not make a lot of difference. So if you have the raw data, the recommendation, of course, is that you should use Excel to generate this output, even though that there is 1 degree of freedom difference because the minor bug that Excel has. Usually, it actually won't make a lot of difference. So this is the first case. This is the case where we have 2 independent samples. However, in practice, we have another case. The other case is what we call match pair. Match pair is this. We take a sample of elements in a population, and we would take 2 measurements from the same sampling unit or from the same elements. For example, if you want to see whether a drug is effective, then you will select a number of patients, and then you measure the blood pressure before the drug is administered, and then you measure the blood pressure after the drug is administered and see whether the drug is effective, right? So by doing so, you're comparing apple with apples. Another example would be that if you want to compare the average price of two stores and see which one is actually has on average higher prices, you don't just go in and take a sample of items in store one and another sample of items in store two and compare prices, because one store you may take really expensive items randomly, and then you in store number two you may take another set of items that are much lower prices. So the proper comparison would be that you take a number of items and then you look at the prices in store number one and prices in store number two, so that you become really literally comparing apple with apples and orange with orange, right? So that is a typical situation when you do comparison um, with this kind of scenario. So how do you tell? Well, first of all, the typical setup is that you have a sample of units from the population, and then you take two measurements from these sampling units. And because of it, the sample size will be exactly the same because they are matched, right? If they're not matched, if the sample size are different, then you cannot really match them up and you don't have a matched pair situation. Now, the interesting thing, of course, is that if you have a matched pair situation, what we really interested is not the measurements of the two measurements that we get from the units. Typically, we are interested in the difference. So when we have this kind of data, what we usually do is, first of all, especially if you do it manually, you would calculate the difference between the two measurements. So we say, take the difference, B2 minus C2, right? So you would do this measurement, and you can actually just copy it down. And now what you're interested in is to really compare the measurement, right? And you want to, if you want to see whether measure one is on average is bigger than the average on measure two, you actually are saying that the difference, because the difference is measure one minus measure two, that means you're saying that the average difference is bigger. And if you're thinking that to try to test whether the mean measurement one is less than the mean measurement two, then you're actually saying that the difference is less than zero on the average. So you are, in this kind of scenario, you are actually convert the problem from two sample into one sample of difference. And because of the fact that we are dealing with one sample, we can use the technique that we learned in the one sample case and apply that to the difference. So if you're doing it in one sample case, remember what we would do. You take the average of the difference minus mu d. Mu d is the theoretical difference. In this case, usually in mu d would be equal to zero. And then you obviously taking into account the variability, which is really the standard deviation of the difference over the square root of the sample size. So that is the concept. So suppose we want to test to see whether the mean of measure one are greater than the mean of measure two. And because of the fact that we are taking the difference between one and two, so we can actually write our hypothesis this way. Mu d is equal to mean difference between measure one and measure two. And what we now want to test is mu d is bigger than zero. Why mu d is bigger than zero? Because we want to test whether the mean of measure one is greater than mean of measure two, and we are taking the difference of 1 over 2. Okay, and so this becomes a one sample problem. Even though that we have two sample, we convert into a one sample problem, and we can use the technique that we learned from the one sample problem to do this problem. Right. So in order for us to do that, first of all, you calculate the mean, the sample mean of the difference, right? So average D2 to D13, right? And then we would take the standard deviation, and again, is STDEV, right? D2 to D13. I'm sorry, the typing is not good. D13, And now let me just use 3 decimal places. Right, so these are the mean and standard deviation, and then we can use this formula, right? D bar is basically the mean, the sample mean of the difference. Mu D is what we're trying to test, and so mu D in this case is 0. SD is the standard deviation of the difference, right? So everything's there. So we can go through the 5-step process. If you go through the 5-step process, the first step, of course, is already defined. Let's see, alpha is equal to, say, 0.05, sorry. The rejection rule, if you're using the previous approach, you will say reject x0 if the p-value is less than alpha, less than 0.05. Right, and the test statistics is calculated as, right, let's just calculate this, right, the mean, which is negative 1.975, which is here, minus mu 0, minus the hypothesized value. The hypothesized value in this case, of course, is 0, right, divided by the standard deviation of the difference, which is 3.128, divided by the square root of the sample size. The sample size in this case is, we have 12 sample units, so divide by 12, and so the t, of course, is equal to 2.1872. And now, how do we calculate p-value? Well, we have, again, draw a picture. This is a upper tail test, so 2.1872 is here, and we want to look at this upper tail area because this is upper tail test. So how do you find the area in the upper tail? Well, you calculate the lower tail and you do it 1 minus, right? So the p-value, let me just write this down for you. Is equal to 1 minus the probability of t bigger than 2.1872. And if you're using Excel to do the calculation, there would be 1 minus t dot dist 2.1872. And now, what is the degree of freedom? Well, the degree of freedom is actually very simple. Right? This is a one sample test of the difference. So if it's a one sample test, the degree of freedom is just n minus 1, as we learned before. N is equal to 12. So degree of freedom is n minus 1. N minus 1 is 12 minus 1. And that's all we have to worry about. Right? So the degree of freedom formula is actually pretty straightforward. And so this is 0.0256. So do we have to multiply the number by 2? Of course not, because of the fact that this is an upper tail test. Okay? So we can now make a decision. We say since the p-value is equal to 0.0256, this is less than 0.05, so we reject x0, right? Now, we know that this problem, the significance of the difference is marginal, because if alpha is equal to 0.05, we reject. What happens if alpha is equal to 0.01? Well, if alpha is equal to 0.01, we do not reject. So this result is marginal, and probably for the most part, the sample size probably is too small. So from a business research perspective, if you have results like this, what we should actually do is to take a much bigger sample size rather than doing that. Now, the confidence interval, if you want to do confidence interval, again, it's really simple. This is a one sample. So if you want to do a confidence interval, if you want to do a 90% confidence interval for the mean difference, and again, this is a one sample case. So what you do is you take the mean of the mean difference, sample mean difference, which is negative 1.975, plus or minus a t value, right? So again, you draw a picture, you have 90% in the middle, right? So So one side, of course, is one side. If it's 90% in the middle, one side is 5%. So you can actually find the value that corresponds to 5% on the lower tail or 5% on the upper tail with a degree of freedom of 11, because the degree of freedom is just n minus 1. So I'm going to use the T table, the T table here, right? So degree of freedom equal 11, area is 0.05, so it's 1.796 would be the degree of freedom. So let me just go back here. So this would be plus or minus, right? It could be 1.796. Did we say 1.796? Yes. 1.796, yes. Right, times the sample standard deviation, which is 3.128, divided by the square root of 12, which is the sample size. That would be the confidence interval. Sorry, I'm going to I didn't type it up properly. So this is plus or minus. Right. So that would be the 90% confidence interval for the mean difference. And so, and what I'm using, of course, is the formula for the one sample case. Now, we can also do, if you want, we can also use Excel. Excel actually has a program to compare population mean using match pair. So let's just do that, right? So how do we do that? We go data, and then we go to data analysis, and then you go to one of the t-tests. It's called pair to sample for means, right? So this is the first one, t-test, pair to sample for means. So this is for match pair, and you say, okay. The input is exactly the same, right? So you will specify the first sample, and then you specify the second sample. So even though the Excel's heading is actually misleading, you call it variable 1, variable 2, you're actually talking about the 2 sample. Also, the labels in the first row. So we'll do that. And then I'm going to put that in here. So I'm going to select and put the output right here. So we can actually compare that, and you say, okay. And here is the okay, and then we can just do some formatting, right? So again, it won't calculate the D bar, but it will give you the mean for sample 1, mean for sample 2. The only difference between what we have seen before and in the last example and here is that you have the Pearson correlation, which is not useful. In fact, we won't even talk about this until the last unit of this. And the degree of freedom, of course, is 11. As I said, the test T6, of course, is negative 2.187, which is exactly the same as what we have done. Again, we have the p-value for one tail, and this is the same as 0.0256, right? So if you actually do, and that's exactly what we have, because we are doing a one-tail test. And this is the critical value if you want to do a one-tail test. And then if you're doing a two-tail test, you can have the p-value and the critical value as well. So the output looks not the same as what we're expecting, because the output does not calculate D bar and SD. There's no way here that you can actually see SD. Don't take the variance and take the difference as SD. That's not right. But what you would use is actually the test statistics that you generate from Excel and the p-value that you generate from Excel. So the two number that is relevant to you if you use Excel is actually these two numbers. Okay, so that's how you also use Excel to perform these hypothesis tests. So for two sample, if you want to compare the population mean, those are the two typical cases. The first case is when we have independent sample. That means that the samples are taken from two independent population. Two independent population means that the population has no overlap. Or you have match pair when you actually take two measurements from the same sampling unit. The last topic we want to talk about is what we call ANOVA. ANOVA is about comparing three or more population means. So, for example, in this example, we have uh, three populations, and we want to see whether the population means from these three populations are the same or different, right? So, for example, this is classical in when this technique is first developed. It was applied in agriculture. You have a field and you want to see different fertilizer and what the fertilizer would do for the yield of a certain crop. So you take the field and you put it into three different pieces of land, and you grow the crop in the three different pieces of land, and you apply the three different fertilizer, and at the end of the year you measure the yield and see whether they're the same, right? So that's a typical situation. In business, for example, you have three different learning methods, and you want um, to see whether the three different learning methods will produce the same results. So that's a really typical situation. And so how do we test? Well, the idea is this: when you have more than two mean, you cannot compare the mean directly, because if you want to compare the mean, you have to compare mean one and two, two and three, and one and three. So it's actually rather complicated. And you want to compare them all at the same time, you actually end up comparing the variances of the population. So therefore, the technique is called analysis of variance. So in this video, we're going to focus on the computational aspect of it. And if you're looking to actually do the test and the computation, the advice is not to do it by hand, even though that for this particular problem, there is a way of doing it by hand. But the computation is so complicated, you should always use a statistical package to do the computation. So Excel actually has a program under data analysis to do this really quickly. So we have three samples. So the first sample has 12 experimental units. We call it experimental units. And the second treatment has 11 experimental units. The third treatment has 9 experimental units. This is actually from obviously the old agricultural days, and that's why we call the name. So actually what it means is that the sample size is 12, 11, and 9. Okay, and so how do we compare them? Well, first we need to generate the output in order for us to perform the computation. And to do that, we go to data analysis, and we go all the way to the top of the list. It's called ANOVA single factor. The factor means that you have treatment is the factor, and you have 3 levels of treatment. Okay, so we say okay, and what we have to do is to specify the input. Now, what you need to do is to make sure that when you specify, you highlight all the data, make sure that your data is covered. So I make this example in such a way that the sample size are not the same, but make sure that you highlight it so that you cover all the data. So here you have space, have no data. Here you have space with no data, but you make sure that you want to cover that, right? So a lot of times in data analysis, your data is not organized this way. So the first thing you need to do is to get your data organized this way. And when you use the data analysis set in, make sure that you cover all the data, okay? And then of course, the data is grouped by columns, and that's basically what we usually do. Again, labels in the first row because we have the name of the variables, of the treatments actually, in the first row. And alpha equal 0.05. So the reason why we specify alpha, because the program is going to generate the critical value at this level. Again, the output range, you can actually specify where the output would be. You can put it in the new worksheet, or I prefer to put it here so that we can show it here. And you say, okay. And actually, that's very simple. Now, let's just make it a little bit bigger so that we can actually see. Let's just make the number a little bit more reasonable. Right? So the output has two sections. The first section is the summary. The summary gives you the mean and the variances of each of the groups. We have three groups, three samples. They are not really useful as if you want to do hypothesis tests. The second part of the output is the key. The second part of the output is called the ANOVA table. The ANOVA table actually has uh, the following components, right? So the first column is called source of variability or source of variation. And so the idea is that you look at the variability between the groups or within the group. So the idea is that if the means are the same and if the variance are all the same, then these three samples are from the same population. So we can actually put it all together. And if they are all the same, then the variability between the groups and between the groups should be reasonably close to each other. So how do we know that the means are the same? You end up comparing the between group variability and within group variability and see they are the same, right? So there are two sources of variability. One is called between group, within group. Uh, in many textbooks, there is also called treatment and error. Treatment and error are obviously from the old situation when we first started developing this technique. So there's two styles of calling either between group, within group, or you call treatment and error because they're actually the same. The important thing is that this table structure is maintained, right? So the second column is called the sum of square. This is basically the deviation between the individual observation and the means or the group means with the overall mean. So this is a kind of measure of the two variability. In order for us to do that, you have to calculate this sum of square. You have to calculate the degree of freedom. So there's two degrees of freedom you have to know. One is the degree of freedom for the numerator. Why is that the numerator? Later on, when we look at the test at T6, the test at T6 are based on a ratio. And so therefore, you have the degree of freedom associated with the numerator and the degree of freedom associated with the denominator, right? And then just like any kind of variance calculation, you take the sum of square divided by the degree of freedom, you get an estimate of the variance between groups, you get an estimate of the variance within groups, and you're comparing the two. And if the null hypothesis is true, that means if the means are the same, then these two ratios should be very close to one. So when is it that we reject the null? When the ratios are much bigger than one. So that's the philosophy. So F is actually the ratio between the two numbers, and F is also the test statistics. So this is called the F test. F is in honor of one of the founders in modern statistics, Sir R.A. Fisher. And then we can, Excel would give you the p-value. If you're using the p-value approach, you can actually look at the number and say, oh, this is a marginal result, right? So the treatments are marginally significant. Why? Because the p-value is 0.04. If you actually run it to here, 0.04. So if alpha is 0.05, you reject. If alpha is 0.01, you do not reject, right? So this is kind of a marginally significant result. So if this is an important problem for you, you probably won't use this as a decision tool. You would actually want to collect data. Excel also give you the critical value, so you don't have to go to the F table to do it. You can actually use it if you want to use the p-value approach. So this is the structure, and you should know about the structure. So a typical ANOVA structure has this, right? The sum of square, right? The two sum of square equal to the overall sum of squares. So you basically take the variability and break it down into between group and within group, or between treatment and error. So SSTR is the name for the between group, and SSE is the name for the within group, and SSTR plus SSE is equal to SST. The calculation of these are pretty complicated, so usually you don't need to calculate them. The degree of freedom for treatment, or the degree of freedom for between group, is actually easy. K is the number of groups. So the degree of freedom for treatment, or the degree of freedom for between group, is number group minus 1. So in our case, we have 3 groups. So 3 minus 1 is equal to 2. On the other hand, the degree of freedom for the within group or error is the total sample size minus the number of groups, right? So now the total sample size means that you have to look at the sample pooled together, right? Because the idea is to, if under the null hypothesis, they are the same, so we pool the sample together, right? So this is 12 plus 11, so this 23 plus 10, so is 32, sorry, 9. So 12 plus 11 plus 9, so is 32. So the total sample size is 32. So so this is 32 minus 3, so is 29. The total, of course, is 31. Right? So the total is actually the total sample size minus 1, so 32 minus 1. Right? So these two numbers also add up together. And then you have the mean square. The mean square is basically like a variance calculation, right? You take the sum of square, divide by this number. You take the sum of square, divide by this number. You get this, right? So you take 76.13 divided by 2. You got this number. 303 divided by 29. You got this number, right? So this is MSTR, so the mean square for treatment or mean square between group. MSC is the mean square for error or mean square for within group. You just take this number divided by this number divided by this, you get these two numbers. And then to test the t-sec is the ratio of these two, right? So the F is actually 38.265 divided by 10.454, right? And because of F is a ratio, so this is the numerator, this is the denominator. So the degree of freedom is called the numerator degree of freedom and denominator degree of freedom. So F has 2 degrees of freedom. One is numerator 2. The other one is the denominator, which is 29. Okay, and this is how you find the p-value, right? And you can actually, of course, you can use Excel function to do it. In terms of graph, F distribution is like this. F distribution is usually like this, but when the degree of freedom is 2 and 29, 2 and 29, it actually change, like become like this, right? So it's always either like this, or when the degree of freedom is small enough, is like this, okay? And the test, if you want to perform the test, is always a upper tail test, right? So this is, there's no such thing called lower tail test or two tail test. The F test is always upper tail test. So let's just, based on this output, we can do a 5-step process. The first step, of course, is write down the null and alternate hypothesis. The null hypothesis for ANOVA is always that all treatment means are the same. And the alternative hypothesis is at least one of them is not the same. So at least one of the population means and is not the same. It is not the same. So that is a typical hypothesis for ANOVA. Now, alpha, of course, we can set it up equal 0.05, it doesn't matter. And the rejection rule, if we want to use the p-value, we say reject x0 if the p-value is less than alpha. And then, of course, the test at t6 is equal to 38 from this table, if you're given this table, is equal to 3.641, right? And now, if you're calculating this, you can actually use Excel's function, right, to calculate the p-value. How do we do that? We say equal f dot dist, right, and 3.641, right, and then you have to specify 2 degree of freedom, degree of freedom 1, degree of freedom 2. So in this case, it's 2 and 29, and then cumulative, right? Now, if you do that, what happens is that you're looking at negative one. Sorry, f is equal to 3.641, and is you have to worry about this area, right? Worry about this area, so you're going to have to do 1 minus, right? And so that number is exactly the same if you actually go back and use this, right? So 0.03883, which correspond to the same, obviously 0.384, right? The same number that you would get from Excel, right? And then obviously, as I said, this is a marginally significant result. Now, if you use the critical value approach, how do you find the critical value? Well, you can either use Excel to find the critical value, right? The critical value would be equal to you can use f.inv, right? And if you want to use, as I said, this is always upper tail test, is 0.05 to 29, and see where we get. Oh, sorry, 0.05. So sorry, this is 0.95. Okay. Now, why is 0.95? Because you're looking at upper tail. So if this tail is 0.05, then this is 0.95, right? So you should 0.95. You get 3.33, right? Which is exactly the same as what Excel would give you. Excel would give you 3.328. Now, you can also use the table. I have reproduced the F table here, just in case you want to use it. So if you use the F table, obviously, as we said, always say you should look at, when you look at the table, you should always look at the graph. The graph says if your area of the probability is given, and you have the 2 degree of freedom, the numerator degree of freedom and the denominator degree of freedom, and the area in the upper tail, then you can find the point that correspond to it. So in our case, we have the degree of freedom is 2 and 29. So we go 2, numerical degree of freedom is 2. Denominator degree of freedom is 29. So we close down to 29, right? Because denominator degree of freedom is 29, right? And then you go across to find the numerator degree of freedom of 2. So it's actually this. Now, there is a block of data here, right? There's a block of data here, right? Why? Because the area in the upper tail could be 0.1, it could be 0.05, it could be 0.025, it could be 0.01, right? So this is one way the table are organized. This is a popular way that the F table is organized. So this is why we are doing this. So if alpha is equal to 0.05, the critical value is 3.33, okay? If alpha is equal to 0.1, the critical value is 2.5. If alpha is equal to 0.01, the degree of freedom is, the critical value is 5.42, right? So this is how you find the critical value. You find the numerator degree of freedom, 2, in this column, and then you find the denominator degree of freedom, which is 29, and so you end up looking at this block of data, and you pick the one that corresponds to the proper alpha, okay? So that's how you find the critical value as well. So now you can say reject x0 if f is bigger than, right? As I said, in the F test is always a upper tail test. So you will say if f is bigger than 3.328. And that's how you specify the rejection rule if you're using the critical value approach. And you can see that the F statistic is 3.641, which is slightly bigger than 3.328. So this is a marginal case, as we talk about. So let me just emphasize the point. The point is that the foundation of doing the F test, of course, is the ANOVA table, and you should actually know about the structure of the ANOVA table by knowing how to identify the degree of freedoms. Right? The numerator degree of freedom is the number of group minus 1. The denominator degree of freedom is the total sample size minus the number of groups. And then you should know about the two mean square calculation, which is this divided by this number, this divided by this number, and then the F statistic is just the ratio of the two estimate of the variance. And that's how we do it. Now, the question is this: if the null hypothesis is not rejected, then there's no further work to be done. If the null hypothesis is rejected, then what we need to do is to find out of the three treatment, which one actually is the highest, which one is different from the other, and so on. And so in statistics, we have something called the multiple comparison procedure that we can apply to do that. However, the multiple comparison procedure usually is outside the scope of elementary statistics, so therefore we are excluding the discussion here. So that's it for this video. I hope that you enjoy it, and I hope to see you next time. Bye for now.